Well, now it's time to show how to do the things in R, and what I'm going to do in this video is to show you all the steps that we looked at in the presentation slide. So we'll make a regression model that will try to predict income by knowing age of person. Okay, and then since in this case I also use the people data, I just decided to copy and paste the first several lines from the previous exercise, from the previous R script, where I just load the people data from Excel file, then solve problem with names and show the first 6 lines in the screen. So they can see that the data is read correctly. So now we can start doing a model. Okay. So first of all, let's make a model, and that's a relatively simple thing. So use function lm linear model, then I will use variable m to keep the result. Okay, so in this case, first you need to say what related to what. First it's a y variable, in this case y variable is income, and then you need to say related to the age, and then say where the data came from. So in this case I use DA. Okay. So that's the model. If you just show the m, you will see the regression coefficients. You can see that this is how the model was created. This is the command you use to make a model. And then these are regression coefficients, exactly the same as we had before, right? So it's 830, it's the slope for the age, and then 1155 or 1156, it's an intercept. Okay. Now let's make a scatter plot. Let's make a scatter plot for this for these two parameters, income related to age, data equal to DA. I'll make them blue. And now you remember that we had a function that is called AB line that can add a line on the plot. Usually we use it for vertical and horizontal lines, but you can actually add a line with any slope and any intercept. And since this object M, where we keep our model, is already containing the intercept and the slope, we can just write AB line M, then let me make it a red color. So I just provide a model, and then AB line understands that, so it will make it will show the line that corresponds to the model. Okay, so that's our model, and you can see that the picture is about the same that we've seen in the slides. Now let's play a little bit. First of all, how to get the predicted value. If you want to get the predicted value for the calibration set, meaning for the points you use to calibrate a model, it's relatively simple. So I will just call them YP, Y predicted, and then you just say fitted, function fitted, and then M returns the predicted value. So if I run it, then I can show, for example, altogether the real values and the predicted ones. So I just bind them together, and then the real values, the real income, and the predicted values, Okay. So just run it. Then you can see that we have 2 columns in this case. So we have the column with real values, income, and then the predicted values. So you can see, for example, Lars, the real salary for Lars is 45,000, but the predicted value is 38,000. Okay. You can actually show the predicted values on the plot by just adding the points. So you just write points. The income will be the same, DA income, and then instead of the real Y values, you can write the YP. Then, for example, let's make them red. Not income, of course, age. Okay, so that's the points. You can see that the points for the predicted values align exactly on the straight line, but that's the meaning, right? So the prediction, it means it's a point on a line. Okay, then you can see, for example, different distances between the predicted and the real values, and this distance gives you an error of prediction. For example, for this particular point, the error will be very small, while for this point, for Lars, the error is quite large. Remember, it's about 7,000. Then, if you want, you can make a new prediction. For example, you know that you would like to calculate the income for age 36. Okay, in this case, it's a bit more tricky, but still possible. So I will call it new YP. Then you use a function predict. The first argument of the function, it's your model, M, and then you need to make a data frame which consists of only one column. It's your X values. So you write data frame, and then the column name should correspond to the names that you use here. So we used age, so the column name should be also age. Then the value, it can be one value or vector of the values. For example, if I use only one value, 36, then I can show the predicted new YP. So if I run it, you can see that's the predicted value. So for if age is 36 and the person is from this population, then from the same population our sample came from, then the salary of this person should be, in average, of course, 28,734 euro per year. If you want to calculate to make new predictions for the several variables, you just do the same. So I will copy and paste, but instead of one value, you can provide several values. C, for example, 25, 35, and 40. Okay. So in this case, this variable new IP will contain 3 values. So this is the prediction for the first, for the 25 years. This is the prediction for the second, and then this is the prediction for the third case. Okay. So that's how to make predictions. Now let's discuss regression coefficients and some inference. Okay. So remember that you can get the regression coefficients by using function show. You can also get them if you use a function coef. And if you just write coef, you will get you will see them. You can also get them as a separate vector. For example, b equal to coef. Then you can see b is a vector with 2 values, minus 1156 and 830. In fact, if you write it here, for example, b. Okay. So you can see that in fact they are they have some decimals as well. Then you can take b1, it will be intercept, and b2, it will be the age. Okay, so that's how to get the regression coefficients. Now the inference, the confidence intervals, and some other inference about the model. Well, let's start with a summary. So if you write summary M, it will show you a lot of interesting things. Well, the table looks a little bit similar to ANOVA, but of course in this case we don't have any like sum of squared values and so on. Let's look at this. So this line, it's a simple thing. It just shows you the how did you call the model, how did you make a model, what code did you use to make a model. This is statistics for your residuals. We will discuss residuals later, but that's the residual statistics. So you can see some the mean, the first quartile, medium, third quartile, and max. And this is very interesting. This is the inference about the coefficient. So in this case, this is the real coefficient, intercept, and age. This is the standard error for your coefficient. And this is the t-value. And you remember we use a t-distribution for the coefficients. They follow t-distribution. And you can use this t-value to make a test. How likely in the population this coefficient is not 0? You remember, if coefficient is equal to 0, it means this particular factor has no influence on y. So in this case we have intercept, and you can see that it's quite likely that for the population we don't have any intercept at all. But you can see that age is important, so the significance for the age is almost 0. So it means that the null hypothesis is that age is not important for the income at all, so the regression coefficients for the population should be 0. But if you make a test, you can see that in fact the p-value is very small, so it's very unlikely that age does not have any influence for the population. Okay, so from this table we just conclude that it seems like intercept could be just 0 for the population, but age is important. Age is important for prediction of income. Okay. And then you have some statistics here. So residual standard error, it's a standard deviation of your errors, right? And you remember we have 30 degrees of freedom because we lost 2 when we calculated the coefficients. Then you can compare with the one that I've shown you on the slides. You can see that it's the same. So it's about 4,000 euro. Okay. This is the r squared, 78%. In this case, you can see that there are 2 r squared values. This one and adjusted r squared. We will discuss adjusted r squared in the next video. So in this case, just look at this one. Okay. And then you also have something that I didn't explain in the lectures. It's called f statistic. In this case, it's a similar thing to ANOVA. We just take the explained y variance and divide it to total y variance. That's the random y variance. That's the f statistics. Okay, and then if f statistic is small, it means that it seems like your model doesn't work. You don't have any explanation of income by using age. But in this case, you can see that the f statistics is very small, and that's the chance to get the statistics, or even worse, even more extreme, if model doesn't work. So that's a very small chance. So this last line just tells you that your model is sound, so your model works. Indeed, there is something. Indeed, we can use age to predict at least part of the variation of income. So that's one way to get the to get the inference about the model and about the regression coefficients. You can also show the confidence intervals for the regression coefficients by using function conf_int, and then also model m. So this is the confidence interval. And by default, it's a 95% confidence interval, and you, of course, can change it if you specify the confidence level you want. Okay, so you can see that, for example, for the intercept, you can see that it can be negative, it can be positive, okay? And it varies quite a lot for the population. But for the age, you can see that the variation is not that large. We got 830 error, but in fact, it should be somewhere between 670 and 990, somewhere in between with 95% confidence, okay? So that's the inference and some statistics, R-squared and standard error. And the next thing we are going to discuss is how to analyze the quality of predictions and how to analyze the residuals, right? So first of all, let's look at the plot that we have used many times in my slides. It's a plot predicted versus measured values. Again, I use the real values as x, it's income, the real income, and then predicted values as y. So this is predicted versus measured values. You can see this is the real values, the real income, and this is the predicted income. And what I don't like in this plot is that the limits are different. So here we start from 10,000 and here we start from 15,000. Let's change this. So we have x limits from 10,000 to, for example, similar 45,000. Then the same y limits from 10,000 to 45,000. Okay, so now the plot is a little bit better. So you can also see that it's not quite ideal, right? We can make an ideal line if we use AB line. You remember ideal line in this case, it's a one that has intercept equal to 0 and slope equal to 1. So 10,000 corresponds to predicted 10,000, 20,000 corresponds to predicted 20,000. So in this case, I just use b equal to 1 and a equal to 0. Okay, so that's the ideal line. So if we have an ideal model, very good model, all points should lie exactly on this straight line. But unfortunately, in this case at least, H is not good enough to explain most of the income. It explains only 78% of the income. Okay, so that's the predicted and measured plot. And the next thing is that let's analyze the residuals. Okay, again, you can get residuals. You can calculate residuals yourself, of course, because you have income and you have predicted values. So just subtract them. Or you can just get the residuals from the model. It calculates residuals automatically. So these are residuals. So I'll just show them. So these are residuals, and residuals, it's a difference between the real value and the predicted one. You can see that for Lars it's about 6,000, for Peter it's 6,700, and you can see also sometimes residuals are negative, sometimes they are positive, right? So let's look at the cuckoo plot for the residuals. And I also add cuckoo line, the theoretical line for the residuals. Okay. So if you look at the cuckoo plot, you see again the same pattern as we discussed before. So the points are more or less line exactly close to the straight theoretical line. You have some, but you have some patterns. You see, you have some patterns, some grouping patterns. So it means that it's not all systematic variation that is captured. Okay. And if you make a Shapiro test for the residuals, you can see that actually they look normal. So it's only 17% chance. It's 17% chance to get a sample like we have, or even worse. So if residuals are normally distributed in population, so it looks normal, and that's what we see here as well. But again, there is a systematic pattern. In the next video, we will discuss how to remove the systematic pattern actually. Then we can also make a plot and see how residuals depends on the real y values. So we make a plot where the real y values will be x and residuals will be y. Residuals. So this is the plot that you can use to see how random the residuals are. Okay, and then you can see this again, this pattern. You can add a line where the residuals is 0, AB line horizontal equal to 0. So this is where residuals should be in ideal case. So residuals should be 0. And you can see that you have both positive residuals and negative residuals. That's good. But you can see some pattern, right? So the same as we discussed before. For example, if you take salary up to 20,000, you see all residuals are negative, right? Then you can see some pattern here. Again, in the next lecture, in the next learning sequence, we will discuss how to tackle this. Because apparently the problem with residuals is the following. Income depends on not only on age. Income depends on several factors. In this case, when we use H, we take into account 78% of variation of income, but still 22% of variation is not explained. So that's why we see this pattern in residuals. If we can explain more, then the pattern will indeed look random.